Thank you for the nice introduction. First of all, I'd like to thank the organizers for inviting me here, and it's my great pleasure to present my work at this wonderful conference. Today, I'm going to talk about indirect reciprocity. By indirect reciprocity, I mean a mechanism to enforce cooperation among people by using reputation system. Well, people cooperate to each other, and a part of the reason is that they don't want to lose their reputation among people. So indirect reciprocity is a really powerful mechanism, but little is known when people have disagreement about reputation. For example, I say someone is a good guy, whereas you think the person is a bad guy, which is indeed realistic, but as far as I know, there is no universal theoretical framework to deal with such a situation. So our idea is to assume or to regard reputation as a continuous variable, because we are not just simply good or bad. Most of us are somewhere in between. And by doing that, the life gets easier, so we can obtain general conditions to stabilize cooperation against two kinds of perturbation. The first kind is mutant norm that have a bit different ideas about good and bad. And the second kind of perturbation is misjudgment. So even if you share the same norm with me, you may assess someone differently from mine because of some kind of perception error. So you may take a good deed as bad or vice versa, and that is another source of disagreement. Well, I don't think I'll have time to cover all these topics, so I'll mainly focus on the first kind of perturbation. Okay, let me give some introduction about this field. It seems that we are hardwired to evaluate people. Even 6 and 10 months old infants evaluate others' actions by observing them. And at the age of 5 or 1, they begin to realize that they are also evaluated by others. So they try to manage their reputations by behaving well to others, especially when they know the interaction is observed. And the reputation management industry is growing rapidly, saying that your online reputation is forever. A bit scary. Well, it was back in 1998 that Martin Nowak and Carl Zygmunt analyzed this indirect reciprocity problem mathematically. And they considered the donation game. This is a special form of the prisoner's dilemma. So here is a large anonymous society, so any pair of people can meet at most once, and they just meet randomly each other. So when you pick up two persons, one guy becomes the donor and the other becomes a recipient, and the donor can choose either to cooperate or to defect. And by cooperation, I mean the donor can give some benefit of amount B to the recipient at the cost of C. So the donor's payoff decreases by the amount of C, whereas the recipient's payoff increases by the amount of B. So B and C are called the benefit and cost of cooperation respectively. And by defection, I mean the donor simply does nothing, so nothing happens. And with probability Q, the interaction is observed by the society. And the image score of the donor increases if his cooperation is observed, and it decreases by 1 if his defection is observed. And the claim by the authors was that cooperation can evolve when the observation probability is larger than the cost to benefit ratio of cooperation. But, well, here comes some criticism. The point is that image scoring focuses only on the donor's behavior. So basically it says that defection is bad even if your co-player is ill-reputed. Then the natural response would be, well, then why should I care about reputation if defection is bad after all? So the alternate suggestion was called standing. So standing, it takes into account the recipient's reputation as well. So its message is that defection is okay if your co-player has bad reputation. So there was some debate between those two ideas. And in 2004, Otsuka and Iwasa made a brilliant idea. So they just checked every possible norms. So out of more than 4,000 possibilities, they checked all the list of evolutionarily stable pairs of social norms when a mutant appears with a different behavioral rule. So here is the list of those 8 successful norms, and these are called the leading 8. And the result says that standing is the winner, because standing is included in this list as L3, whereas image scoring is not, because the key difference is like, okay, I'll explain the notation. Here, assessment rule is, this is the rule used by the observer, and it is denoted as alpha, and alpha is a function with 3 inputs. So the inputs are the donor's reputation, donor's behavior to the recipient, and the recipient's reputation, and it is a binary function giving us 1 or 0. And 1 means the donor gets a good reputation. 0 means the donor gets a bad reputation. And behavioral rule is denoted as beta, and it is, again, a binary function accepting 2 inputs, and the inputs are the donor's reputation and the recipient's reputation. So it prescribes whether to cooperate or to defect if donor and the recipient have certain reputations. So according to that, the fundamental difference between the leading 8 and the image scoring is here. So it means if a good donor defects against a bad recipient, it should be regarded as good, which image scoring does not satisfy. So that's why image scoring is not stable against a mutant which behaves differently. But the point is that they considered only the behavioral mutants, so the assessment rule is shared by all the members of the society. Of course, this is highly unrealistic, so if this agreement appears, we run into big trouble. Here is an example I took from Hilbe. So suppose we have 3 players, and player 1 and 2 are the donor and the recipient. They are interacting, and player 3 is observing that interaction. And for some reason, player 3 suspects that player 2 is a bad guy. And he observed the cooperative interaction from player 1. And well, this player is a rather strict guy, so he thinks even this player 1 is a bad guy because he is helping another bad guy. So in this sense, this agreement spreads, and it lowers the overall cooperation level of the society. And I told you there is no universal theoretical framework. There are only case-by-case studies. With this strategic configuration, we end up with this result, but with a different configuration, we have a different result, and so on. Okay, so let me move on to our model. Okay. So there are some reasons to introduce continuity. Empirically, dichotomy is not enough in assessment. This has been reported several times by social scientists, especially Olin said questions with more categories are more reliable and more valid. this guy was studying how many categories are necessary for an effective questionnaire. And the second reason is something operational. So when you consider error introduces probabilistic mixing. By mixing, I mean, if one makes a mistake with 10%, then the average donation would be 0.9b, which is a continuous number anyway. And the final reason is methodological. So if you allow a continuous variable, it allows us to use a small parameter to develop a perturbation theory, looking like that. If we have only 0 and 1, this is simply impossible. Okay, now this is an important part and a little more mathematical. But the idea is basically easy. This is a simple generalization of the idea from Oshik and Iwasa. So let mki of t denote player k's assessment of player I at time t. And now this is a continuous variable between 0 and 1. So if this takes value 1, it means k regards I as totally good. And 0 means, well, this guy is totally bad. And of course, most of us have somewhere between 0 and 1. And beta, this is the behavioral rule of player I. So it has the subscript I. And it says donor I's donation level to its recipient J. So it considers two factors. One is self-evaluation. Okay, how donor thinks about himself. And the second input is how the donor thinks about the recipient J. And this is again a continuous function between 0 and 1. So the donation game looks like this. B times beta I will be donated by donor I at the cost of C beta I. Yeah, so beta I works as a weighting factor of the donation gain. And as before, alpha, this is the assessment rule, but this is now alpha sub k, so it means observer k's assessment rule. And it's again a function of three inputs, like how the observer thinks about the donor and what the donor did and what the observer thinks about the recipient. And now we can write down an average dynamics of reputation. So at the next time step, the assessment can change if the interaction between I and J was not observed, then it will take the previous value with the probability 1 minus Q. But if it is observed, then yeah, it is updated by this assessment rule. But you see, the left-hand side doesn't have any index for the recipient J. So I took an average over J. This is a simple-minded approach. So, and this is the basic equation that I should work with. And yeah, this looks little informative at this stage, but let's keep moving on. And to make the formulation a little more informative, I will add further assumptions. First of all, the social norm should be able to maintain cooperation and good reputation. So it has this fixed point. And we will take this fixed point as the initial condition. So the deviation from this initial condition will serve as small parameters for the perturbation theory. And since everything is now continuous, we can take differentiation, and those partial derivatives tells us how those social norms are, how those social norms respond to the change of each input. So in that sense, it gives us sensitivity measures. For example, A of X means how the assessment rule of the society reacts to the change of the donor's reputation and so on. Okay, with this tool, I will analyze the stability against mutation. Okay, first one is some empirical observation. Social norm, well, at its core, it has a certain circular reasoning. So following a social norm is good, and a collection of good things are, it somehow defines the social norm. So it makes somehow a circular reasoning, and by means of such a circular reasoning, it can resist changes. So here is a figure, and this is a norm about how to spell a word. And with the intervention from the government, it takes about 2 decades to change the spelling from C to Q. But without intervention, the norm doesn't change much, so it often takes centuries just to use a different word for the same thing. So in that sense, I want to argue that most changes are small modifications to the existing norm. And with this statement, I want to restrict my focus to small mutation. So let's say the resident norm is denoted as alpha and beta, and some fraction p of mutants deviate by adopting a different social norm, and the deviation is defined by delta and eta, and those are small in magnitude. And we'll consider only stationary state, then we get this kind of equation of reputations. So if the set of assessment rules and behavioral rules are given, then we have to solve this equation of reputation self-consistently. And well, let's expand alpha and beta to the linear order. Then we get a system, a linear system, a 4-dimensional linear system, which we can readily solve. And those delta and eta, they are characteristics of the mutants. And let's just solve it. And then it will tell us how much payoff the resident and the mutants will get. And the result is like this. So the mutants' relative advantage in payoff is here. And this is just algebra. And a nice thing about this expression is that all the mutant properties are inside this square bracket, and it doesn't change the sign. Only the relevant factor to change the sign is here, and it is independent of the mutant property. So in order to make the mutant suppressed, then the only inequality to satisfy is here. And this is in terms of only the residence norm properties. So as long as the mutants are small modifications, we can say something very, very general. We don't care about its specific properties. And our numerical simulation agrees well with our prediction. Our linear prediction is here, whereas the numerical results have a crossing point somewhere around here. And if we add high order terms, the agreement becomes even better. And here Q is the observation probability as I defined before. And when the perception error is absent, the observation probability doesn't affect the result, contrary to the prediction by Nowak and Zikmund. Well, when the perception error exists, it has some effect, but I say the effect is rather minor. It doesn't change the overall picture. Okay, so from this analysis, you can say the stability condition is this inequality, and this is a fairly general result if we restrict ourselves to small mutation. And we have good reason to say that AX is 0. So let's forget about this denominator. Then the relevant factors are AY and BY, and they have very clear meanings. So AY it tells us how sensitive the assessment rule is to the observed action. So if someone decreases his cooperation level, then we should take that into account when assessing the donor, which is quite obvious. And BY is something about the behavioral rule. So if the recipient's reputation is bad, then I should decrease my donation level, which is also plausible. So by those two factors, the necessary cost to benefit ratio of cooperation is determined. Okay, how many minutes do I have?
7 minutes.
7 minutes.
8 minutes.
8 minutes.
8 minutes, sorry.
Thank you. All right. In fact, I have swept something under the carpet. So when I apply the linear analysis, it encounters singularity when it is applied to the leading edge. I don't know why. I'm still working on that. But a clear thing is that we need a high order analysis to apply our theory to the leading edge. So we have to solve a set of coupled nonlinear equations, which is not easy, but we are making progress. So yeah, here are some numerical results compared with our approximate solution represented by the dashed lines. And we also need some regularization parameters to control the singularity. Yeah. So the point is that there are still many missing points in our analysis, even though in the end it may look quite nice and simple. I don't understand very many things at this moment. Okay, this is another kind of stability. As I said, the assessment error may also perturb the system, and in this case, the stability condition becomes quite different. But well, it cannot be done within my limited time, so let me just skip this part. Okay, to summarize, indirect reciprocity is a mechanism to enforce cooperation based on reputational information. But the key point is this information is very, very often incomplete, erroneous, and processed incoherently. It simply differs from person to person. And our continuous model helps to deal with incomplete observation by choosing Q less than 1. And we can also deal with error. And this is basically a source of the probabilistic mixture. And we have also dealt with mutants. The restriction is that the mutants must be close to the existing norm, but I think we can somehow justify this assumption to some extent. All right, this is it. And if you are interested, please check our recent papers here. Okay, thank you for the attention.
Thank you very much for the very interesting talk. Are there any questions? Yes.
Right, thank you very much for very nice talk. So I wonder, you skipped the computation part, but you introduced the equation, time evolution equation for m sub kit.
Yes.
And that seems to me that related to the assessment of k about I, that evolving with time. So when you solve that equation in the bottom, then so what do you do? So you assume that everybody is connected to everybody, and then
yes,
and then you proceed. All right. So then can I consider that as a sort of mean field calculation?
Yes, exactly.
Oh.
And as for the computational part, here we are simulating an agent-based model.
How many?
It's not so many, and it doesn't have very big size dependence. So
I see.
consider only population of size 50 or 100.
Oh, I see. All right. Okay. All right. Thanks.
I think we have time for 1 or 2 more questions, if there are any. So, if I may, exactly in this slide, so you say that the relative advantage is independent of the mutants fraction. So in a sense, whether the mutants gain more or less compared to the other, to the non-mutants, it doesn't depend on the number of mutants. But does the actual evolution depend on the number of mutants? So in a sense, can there be sort of a critical ratio of mutants that the mutants win anyway, even if they don't have a relative advantage?
Yeah, that is another point that I don't quite understand. This is just an algebraic result that I got, but for some reason the fraction p is exactly cancelled with, from this expression. And of course, I must emphasize that this is only true for close mutants. So if the mutants are very far from the resident, then we cannot say that, of course. Yeah.
And so does this also remain true to higher order? So you mentioned also going to higher order. Does this still?
No.
Okay.
This is only true for the linear analysis.
Okay. Thank you very much. So if there are no other questions, then let's thank the speaker again.